Yeah.
Take it away.
Can you see my notes right now or not?
Yes, you
Yeah,
had
we can.
a minute ago was better. You had it the right way.
Yeah, a minute ago I couldn't see my own notes.
Oh, well, that doesn't help.
Let's do this.
There you go.
Now?
Yeah, we see just your slides.
Awesome. Okay. Yeah, anyway, I'm here today to talk about my project ManyDAGs, a consensus-based approach to causal inference. This is some data. It's data on ice cream consume and drownings. So on the x-axis, you have the month of the year. And on each of the y-axis, you have the ice cream amount in kilometers eaten in a year and the number of deaths by drowning. And what you can see is that during some months, both of them are higher. So in data, we have a correlation. Now, as scientists, we sort of want to explain why we have this correlation. It could be that ice cream consumption causes drownings. Maybe people eat so much ice cream that when they afterwards go swimming in the ocean, they're too heavy to keep themselves over water and they drown. Alternatively, maybe the friends and family of people who drowned are so sad that they eat a lot of ice cream, which creates this correlation. Or maybe there's a third variable, such as temperature, that affects both ice cream and drownings. Now, all of these three models I show you here are so-called causal models. They are a causal display of the variables we think are important in a relationship between two variables and how these variables are causally related to each other. In this first graph, I only have two variables, and I think one causes the other. Same in the second graph. There are only two variables, and I think one causes the other. Here, there are three variables, and I think temperature causes both ice cream consumption and drownings. Now, if you went through research methods training in psychology, people probably taught you that the only way to establish causality is to do an experiment. So if I want to know if ice cream consumption causes drownings, drownings cause ice cream consumption, or there's maybe an alternative explanation, I would have to manipulate one of my variables. For example, I can manipulate ice cream consumption. I can feed a lot of ice cream to half of you and not to the other, and then I can send you swimming. Alternatively, if I think drowning is the independent variable, I can drown half of you and then look at how much ice cream your families eat. And this sounds pretty ridiculous. But the point is that we often want to test causal theories. We have causal theories about how humans work, why humans behave the way they do. But we cannot test this experimentally because experimental tests of these theories might be unethical, impractical, or straight out impossible. And what psychologists often default to doing is they have that neat correlational data, they have their causal theory, and then they interpret their correlational data as causal, but they include one sentence somewhere in the discussion that you shouldn't interpret their data as causal because it's correlational. And then the next sentence, they again talk about the causal implications of their model and their data. That is, of course, not super satisfying. What psychologists also like to do is they like to come up with some form of lab-based experiment to test the processes underlying this. But these lab-based experiments are often not super generalizable, and they don't really reflect how the real world works. So what can you do if you want to make causal claims from correlational data based on the real world? Well, what you can do, and luckily we are not the first research field to run into this, you can use the tools of causal inference. Economists, political scientists, and computer scientists have established many really cool methods for how you can go about establishing causality in observational data. Now, these approaches differ in how mathematically sophisticated they are, and each of them have different assumptions and issues. But at the heart of each of these methods lies a causal model, like the three models we drew here. Now, I'm not actually a methodologist. I'm an implicit bias researcher, and the type of research I do is in the field of regional psychology. So what I do is I investigate how regional variation in implicit bias is associated with regional variation in other factors. For example, in past studies, I looked at how a history of slavery, a history of Ku Klux Klan presence, a history of sundown towns and Native American boarding schools is associated with modern-day racial bias towards Black people or Native Americans. Now, the theory underlying all of my research makes causal predictions. It states that the social and cultural environment affects people's attitudes about social groups. Yet, I will never be able to experimentally test this. I can't randomly assign people to live in regions. And even if I could, they would probably not stay in the region where I assigned them to. So what I do in a lot of my work is I draw causal models like the ones I showed you before. And I see if, based on these causal models, I can come up with ways in which I can establish causal effects, given particular assumptions. One research question that, for example, has been investigated in the field is whether the presence of a Confederate monument in a county causally affects people's implicit bias. So if I draw this as a causal model, I would have a node for Confederate monuments, I would have a node for racial bias, and I would have an arrow going from Confederate monument to racial bias. This arrow indicates that I think that the Confederate monuments causes racial bias. Of course, there might be variables that also play a role in this relationship. For example, regions that have more Black people in them are more likely to have Confederate monuments, because Confederate monuments were predominantly built in the South, where there was a strong history of slavery, and therefore relatively more Black people. Proportion of Black people in an area is also linked to racial bias. We know from contact theory, for example, that having intergroup contact with an outgroup leads to more positive intergroup outcomes, including racial bias. Other scientists might believe that education plays an important role in this relationship. More educated people tend to be less biased, and more educated people might know that Confederate monuments symbolize racial hatred and were built as symbols of white supremacy in the 1940s and don't really reflect Southern heritage. So they might believe that education is an important variable. Now, the problem I as a researcher face is that all three of these causal models are possible and valid. And there are very few options with data in which I can show that one of these causal models is right or wrong. A causal model and picking the right causal model therefore depends on your theoretical argumentation. And different researchers can arrive at different causal models based on different theoretical argumentations. In time, if you have different causal models, you might run vastly different analyses and therefore have vastly different research findings. And in this project, it was born out of spite mostly. Whenever I submitted a paper, there was a reviewer who wanted me to add his favorite covariate to my model, even if I thought that covariate didn't make all that much sense. But it's very difficult to argue against the inclusion of such a covariate, because it could just be that this reviewer has a different causal model of reality than I do. And who's to say that my model is right and his model is wrong? So what I wanted to do is I wanted to create many, many causal models for the same theoretical research questions by many, many different scientists. And I wanted to see where these causal models overlap. Do people think the same variables are important? And do people think that these variables have the same causal relationships to each other? To investigate this, I recruited a large number of experts in regional psychology. Regional psychology is a relatively new research field. I would say there are about 50 or 60 people active in it, and we got more than 35 of them to participate, including the biggest researchers in the field. As a second step, we taught all of these content experts in regional psychology what a directed acyclic graph is, so how to draw a causal model. And we taught them also how to create realistic causal models and how to draw them. Followingly, we gave each of these, my slides stopped working, here we go. Followingly, we gave each expert and their team 2 research questions. And we asked them to draw the causal model corresponding to this research question. And lastly, we evaluated each of these causal models, and we looked at what variables they used, and what causal relationships these variables are to each other. And more importantly, if based on this causal model, we can establish a causal effect in one way or another. Now, the 2 research questions we gave our experts were, what is the effect of the presence of a Confederate monument in a county on the racial bias of white people in that county? And second, what is the effect of white people's racial bias within counties on Google searches for racist terms within that county? Now, next, I will show you some of the causal models people drew. One researcher drew this causal model. So you have a node for Confederate monuments and you have a node for racial bias and an arrow between them. So he thinks Confederate monuments causally affect racial bias. He also thinks that there's some institutional racism variable that causally affects both the presence of a Confederate monument and racial bias. And lastly, he thinks that whether there's a Confederate monument and whether there's institutional racism depends on whether there was some big historical event like a battle during the Civil War there at the time. For this causal model, for example, the implication is that I can establish a causal effect if I just control for institutional racism, because institutional racism is a so-called confounding variable that affects both the independent and the dependent variable, and therefore might bias any correlation between them. So if we can control for that, according to this causal model, we can estimate a causal effect. Now, these are just 4 variables, and other researchers came up with slightly more complicated causal models with many, many more variables in between them. Now, what variables did researchers think are the most important? Well, 40% of the causal models we got contained the variable education on a regional level. 40% contained the variable political orientation, and 33% contained the variable segregation. These are the variables that were mentioned most often. So what we can already see is that even people with a lot of substantive expertise in a super narrow subfield of psychology can't really agree on what the most important variables are. Most DAGs sort of had 10 variables, and many of these variables were only mentioned by 1 or 2 of the expert teams. Now, next, I want to go over all the different ways in which we can establish causal effects based on these DAGs. The first way we looked on is the so-called backdoor criterion. And the backdoor criterion simply states, if you can close all backdoors through which your variables of interest are related, you can establish a causal effect. For example, on the DAG displayed here, we have a direct error from Confederate monument to racial bias. This is the causal effect we want to estimate. However, there's a third variable, proportion of Black people, that affects both the independent and the dependent variable. And because it does so, it can create spurious correlations between the dependent and independent variable. in data, that means these variables could be correlated, even though they're not correlated in real life, just because they have this common cause. What you can do, for example, in your linear regression is you control for proportion of Black people by including it as an additional variable in your regression. And when you do so, you close this backdoor. Now, in our data set, we had 15 expert teams who each drew 2 DAGs, so 30 DAGs in total. 27 of these 30 DAGs fulfilled the basic criteria to be called a DAG, and 19 of these 27 had at least one set of variables you can control for to fulfill the backdoor criteria. Again, the 3 variables that were named most often that fulfilled the backdoor criterion were education, political orientation, and segregation. So the variables most people thought of are also variables that together can fulfill the backdoor criteria. For example, if you look at this DAG here, you again have an arrow from presence of Confederate monument to white residential racial bias. And this again is the causal defect we're interested in. However, you also have the variable conservative political ideology that affects both the independent and dependent variable. And you have the variable Black-white socioeconomic inequality that affects white resident racial bias and is via a collider structure associated with the independent variable. So if you here in a regression, again, control for both of these variables, you could estimate a causal effect. Now, the second type of way in which we looked at whether we can estimate a causal effect from the DAGs we got was by looking at whether we can identify unconditional instruments. For example, say you're interested in estimating the causal effect of a variable D on a variable Y. However, you know that there are variables here, V, that you do not have data for. And because you do not have data for these variables that are a common cause of D and Y, and therefore can create spurious associations, you cannot control for that. However, if you find any variable Z, so that's called an instrument, that is not confounded and only affects D, you can use some fancy math to estimate the causal effect of D on Y by using Z as an instrument. Of the DAGs we received, 20 of the 27 DAGs we had, 6 of them had an unconditional instrument. For example, in the DAG you see here, you see that racial bias causally affects Google searches, but that there are variables, income, age, political orientation, education, population density, proportion of Black people, and employment rate that affect both racial bias and Google searches according to this causal model. And if you don't have the data for any of them, you can't control for them. However, you can also see that there's a variable called racial contact, which is not affected by anything else, but affects racial bias. So following the causal model drawn by these researchers, racial contact could be such an unconditional instrument. Secondly, we also looked at the number of conditional instruments. Conditional instruments work the very same way as unconditional instruments, just that there's a variable C that confounds your instrument with the unobserved variables. However, if C is observed and you can control for it, you can close this backdoor through C and then still use that as an instrument to estimate the effect of D on Y. Here, 11 of these 27 variables, 27 DAGs had a conditional instrument. For example, in this DAG here, you have a variable racial related event that causally affects both activated associations and Google searches. And you have activated associations that affects racial bias. So you can use activated associations as an instrument to look at the causal effect. To sort of bring it together, most models drawn by the researchers in the field of regional psychology allow for the identification of a causal effect. However, there's very little agreement between different research teams on which variables to include and what causal role these variables play. That means I unfortunately cannot use this project to give to a reviewer and say, look, my causal model is better than yours. Also, many of you probably participated in many analyst projects or have heard of many analyst projects. And what you often see is that there's some huge variation in effect sizes. What we show here is that people already have huge variation in the causal models underlying the interpretation of research questions. And if people have very different causal models, they also use very different analysis to analyze their data. So these many analyst projects might not actually reflect that different analysis give different results. They might just reflect different causal models underlying the different analysis. Now, I did this project together with Jimmy Calanchini, who's an expert in regional psychology, and Felix Thomas, who's a professor of causal inference. Thank you very much for your attention and enjoy the rest of the conference.
Awesome. So, what do you do since they all disagree?
That's a good question. I think what I might do is just try out different causal models and see whether the causal effects you can establish based on them converge. Sort of, again, taking like a multiverse approach to this.
Yeah, Amelie, go ahead.
Hey, thanks, Max. So I guess also with your point on many analysts, I guess if someone was planning a many analyst, you would possibly integrate asking teams to draw a DAG into your data collection.
Yeah, I think that would be super interesting because maybe there are some ways in which you can quantify what aspect of the variation in effect sizes is due to the differences in causal models and which is actually due to the differences in data analytic approaches. I think there was a comment by Ausburg and Brüderle on the first many analyst paper by Silbertzahn, where they showed that analysis which had more closely corresponding interpretations of the research questions showed more similar effect sizes compared to the general sample.
Okay, thank you. Also, just as a semi-joke, I note that spite is truly the real academic motivation.
No, it's a great motivation.
Yeah, no, I approve fully. That's not a dig.
Yeah, I don't know if that's how you pronounce the name, Aaron, but Silberzahn means silver tooth in German. It's just two German words put together.
Okay.
That's why I pronounce it German.
I'm sure that's right. I mean, I think we say something like Silberjan or something, but I was just like, oh, I'm mispronouncing that. Anytime I see a Dutch name, my brain just immediately is like, because I know I'm gonna get it wrong. But
yeah, my advisor is called Gijs Bijlstra, and you spell that Gijs, and nobody can ever pronounce this.
Yeah, my brain would freak out.
Yeah.
I saw some folks pop in. Questions for Max?
No, wonderful. Then my workday is over.
Love that. All right, here, let me hit stop.